The outer region around Asteroid Bennu sits within a wide and quiet part of the solar system, where space stretches in every direction, with long arcs of dust-sparse fragments, and the distant glow of sunlight that weakens slowly with every additional stretch of distance from the Sun. Bennu moves within this area as a small carbon-rich body, whose size is modest when compared with the larger asteroids that occupy the main belt farther outward. Its presence here is defined not by activity, or by familiar patterns usually associated with planets, but by a slow and steady drift shaped by the gravity of the Sun and by the faint gravitational touches of nearby worlds. The setting around Bennu is almost entirely empty when measured in ordinary terms. Every object remains separated by vast reaches of space, measured in numbers that require patience to imagine, and Bennu's body passes through these reaches without disturbing anything around it. The light that reaches its surface travels outward from the Sun, across long stretches, becoming softer and cooler as it arrives. This light shapes the rhythms of Bennu's rotation, its temperatures, and the gradual release of heat from its uneven surface. In these outer surroundings, the main elements that define the environment are distance time and the slow interaction between sunlight and matter that has existed for billions of years within the solar system. Bennu itself is small enough that it does not significantly change the landscape around it. Instead, it behaves like many of the primitive bodies that formed early in solar system history, retaining much of their original material because their low mass prevented deep internal heating or reworking. The wider region remains calm with neither storm nor atmosphere nor liquid. There is only vacuum sunlight and the occasional passage of tiny dust grains that drift along long orbital lines. Bennu follows an orbit around the Sun that carries it near Earth at certain times, but this broader space remains mostly unchanged by those encounters. The gravitational pull of Earth alters Bennu's path only slightly, and the asteroid continues onward along its long loop without deviation from the slow pace set by its size and the Sun's gravity. In the outer zone where Bennu travels, the Sun appears smaller than it does from Earth, giving off a colder and less intense illumination that still guides the asteroid's behaviour. The faint warmth that reaches Bennu creates small temperature differences between its sunlit and shadowed sides, and this difference contributes to a process in which reflected heat exerts a gentle force. This force, called the Yarkovsky effect, pushes the asteroid with a very small amount of pressure, slowly altering its orbital path over long intervals. Although this effect is weak, its influence becomes noticeable when considered across many years, especially for objects as small as Bennu. The solar system's outer neighbourhoods where Bennu moves include dust made of carbon silicates and fragments of older bodies that broke apart through collisions. These collisions happened far earlier in solar system history, leaving behind debris that continues to orbit the Sun. Bennu's path crosses some of these regions, although the space between particles is so wide that impacts are rare. The asteroid's surface reflects only a small amount of sunlight because its material is dark and rich in carbon. From a distance, it appears as a dim moving point that blends with background stars. Observations from spacecraft and telescopes show that its brightness changes slightly as it rotates, giving hints about its shape and surface features. This outer region is also a place where gravitational perturbations accumulate. Each pass near a planet modifies the path by small increments. Over long timescales, these interactions shift the orbit gradually. Bennu's present-day position results from countless such small influences. In these surroundings, Bennu completes one orbit around the Sun in a period lasting a little over one Earth year, yet the way it moves through space feels slower because distances expand outward across hundreds of millions of kilometers. The outer region offers no medium to carry sound or wind. Thermal energy moves only through direct radiation. Bennu's ability to hold heat is low because its surface is covered by loose rubble that does not conduct thermal energy efficiently. Sunlight warms the upper layers during the asteroid's daytime, and these layers radiate that heat away during nighttime. This pattern maintains a predictable thermal cycle in the outer region, though the temperature values shift depending on Bennu's distance from the Sun at different points in its orbit. The wide setting also determines the frequency of micrometeorite impacts. Small grains sometimes strike Bennu's surface at high speeds because the thin dust population continues to circulate around the Sun. These grains alter the outermost millimeters of material, darkening the surface over time and loosening particles that may drift or fall into surrounding crevices. Although these effects are small, they contribute to the slow evolution of Bennu's surface in the outer region. The asteroid retains most of its original material in part because the outer region lacks strong heating sources or environmental disturbances that would modify its composition. This quality makes Bennu valuable for scientific study because carbon-rich asteroids may provide information about early solar system conditions, including the distribution of organic material and minerals that interacted with water. The outer region where Bennu travels also includes the gravitational zones of nearby planets, which cause gentle shifts in orbital inclination and eccentricity. These shifts occur gradually and do not change the overall stability of the orbit, but they do influence long-term predictions used to determine how close Bennu may approach Earth in future cycles. From this outer vantage, Bennu remains one among many small bodies that circle the Sun in relatively stable patterns. The asteroid's size, density, and composition allow it to withstand the constant exposure to solar radiation without major alteration. Any internal changes occur at a pace defined by the slow movement of heat and the occasional seismic disturbance caused by impacts or thermal expansion. These events are minor compared to the asteroid's total mass, but illustrate how objects in the outer solar system maintain their structure over long spans of time. Bennu's presence in this region allows spacecraft to approach it safely, because the lack of atmospheric drag magnetic fields or strong dust activity means that missions like the one conducted by NASA can study its surface closely. The outer zone provides a calm backdrop for observing the asteroid's rotation rate, surface reflectance, and spectral features that reveal the types of minerals present. The region itself acts as a natural laboratory, where stable conditions allow precise measurement. The faint sunlight, steady gravitational field, and low particle density form a constant environment against which Bennu's features appear clearly. Over time, the asteroid continues to move along its orbit with a rhythm determined by the interplay of heat, gravity, and rotation. Its slow spin brings different surface regions into and out of sunlight, creating a predictable thermal pattern that influences the outer layers. The wider region remains quiet as Bennu continues its long journey around the Sun, carrying with it evidence of early solar system material preserved in its carbon-rich structure. No sudden changes occur here. Only the patient shifts defined by physics shape the environment. Through this calm and steady setting, the asteroid remains a stable point of study for scientists seeking to understand the earlier stages of planetary formation. Bennu follows an orbital path that stretches into a long and gentle ellipse around the Sun, shaped by the combined influence of solar gravity, the asteroid's low mass, and the slow push of thermal forces acting across many years. This orbit does not remain fixed in space, but shifts gradually as sunlight warms one side of the asteroid during its daytime, and allows the warmed surface to release heat during nighttime. That release produces a faint recoil that nudges Bennu's path in ways that accumulate significance only over long spans of time. The asteroid's journey along this path carries it across regions where the gravitational pull from Earth and other planets becomes slightly stronger, producing additional adjustments that change the orbit's tilt and its distance from the Sun at different points. These changes occur so slowly that Bennu continues to move with a steady and predictable pace, completing each loop around the Sun in a period that lasts a little longer than one Earth year. As Bennu travels, its motion reflects the balance between its rotation and its progression along the orbital line. The asteroid spins at a rate that brings each surface feature into sunlight and then into shadow, within a period a little longer than 4 hours. This rotation allows heat to move across the surface at a regular rhythm, maintaining temperature differences that feed the thermal force responsible for gradual orbital drift. Although these forces are weak in magnitude, they matter for a body as small as Bennu because its mass is low enough for minor pushes to cause noticeable displacement over time. Observations made by spacecraft reveal that Bennu's orbit is slightly shifting inward. consistent with expectations for a carbon-rich asteroid that absorbs a significant portion of incoming sunlight. The outermost layers retain heat long enough to radiate energy back into space in a direction that influences the orbital path. As Bennu continues this pattern, its distance from the Sun changes slowly, though the orbit remains stable without signs of rapid alteration or fragmentation. The orbital line brings Bennu near Earth on intervals set by the relationship between the lengths of their respective orbits. During these close approaches, gravitational interactions provide new data for refining long-term predictions of the asteroid's path. Measurements of its position become more precise when the asteroid is observed from multiple vantage points, allowing scientists to track how Bennu responds to small gravitational influences. These influences include the pull from Earth, the gentle tug from the Moon, and contributions from other planets whose gravity spreads throughout the solar system. Bennu's orbit also crosses the plane of the solar system at an angle that changes slowly over time. This inclination determines how often the asteroid passes through regions closer to Earth. The stability of this pattern results from the interplay between the Sun's dominant gravitational force and the weaker forces that adjust the orbit's shape. Bennu's motion can be described as a steady glide along a path that has been shaped over billions of years of subtle gravitational interactions involving countless bodies. At any moment, Bennu's position can be calculated with high accuracy because the physical processes that control its motion follow known principles. Its velocity shifts according to its distance from the Sun. When closer to the Sun, Bennu moves more quickly because the gravitational field is stronger. As it drifts outward to more distant parts of the ellipse, its speed slows, reflecting the same principles that govern the orbits of planets and other small bodies. Bennu's orbital behavior becomes particularly important when projecting its position into the future. Over decades and centuries, the combined effects of thermal radiation and gravitational perturbations create pathways that branch into multiple possibilities. These possibilities remain within known boundaries, allowing scientists to determine intervals during which Bennu will pass close to Earth. Although some of these intervals present very small impact probabilities, the overall stability of the orbit indicates that Bennu remains a predictable object whose movement can be monitored with increasing precision as more data accumulates. The asteroid's orbit exists within a region of near-Earth space where many small bodies follow similar paths. This region forms a dynamic environment in which sunlight, heat, and gravity interact without interruption. Within this environment, Bennu's motion is mostly quiet and unchanging, though precise enough to serve as a test case for refining models of orbital drift. These models are crucial for understanding how other carbon-rich asteroids behave, particularly those with low density and high surface porosity. Bennu's orbit also defines its exposure to different temperatures. When closer to the Sun, its surface warms enough to increase the magnitude of the thermal recoil force. When farther away, the surface cools and the force weakens. This cycle creates a long-term pattern in which the asteroid steadily shifts its orbital position over generations. The direction of this shift depends on factors such as rotation direction, thermal conductivity of the outer layers, and the distribution of boulders and fine grains across the surface. Observations from spacecraft show that Bennu's shape, surface slopes, and distribution of dark material influence how heat moves across the asteroid, which in turn affects the precise direction and strength of the thermal push. The orbital path presents additional interest because Bennu belongs to a class of asteroids thought to have originated much farther from the Sun. These bodies often travel along routes that bring them near Earth after long intervals of inward migration. Bennu's current orbital distance places it in a range where sunlight reaches the full surface during each rotation, allowing the thermal processes to continue in a stable rhythm. Its relatively low eccentricity ensures that temperature variability remains within predictable limits. This stability supports accurate modelling of its future behaviour, though small uncertainties persist due to the complex interplay of surface features and heat flow. Understanding the orbit requires precise tracking of the asteroid's centre of mass, which lies within its loosely bound interior. any shift in internal distribution could slightly alter how the asteroid responds to gravitational forces. Yet available observations suggest that Bennu's mass distribution remains steady, allowing consistent orbital predictions without evidence of major internal reorganization. Over time, Bennu continues moving through space along its elliptical route, crossing regions of slightly varying solar intensity, dust density, and gravitational influence. The simplicity of its motion reflects the calm of the surrounding environment. No major disturbances arise to alter its path dramatically, and the basic structure of the orbit remains intact from one cycle to the next. This continuity creates a stable context in which scientists can study how small bodies respond to the gentle but persistent forces present throughout the solar system. Bennu's orbital path thus serves as both a record of past influences and a guide to future motion. As long as sunlight reaches its surface and gravity continues to shape its trajectory, the asteroid will maintain its steady progression along the same broad curve. The details of this motion reveal how small forces accumulate over long times, how ancient material responds to modern conditions, and how bodies like Bennu define the subtle yet precise patterns that govern the outer layers of near-Earth space. The origins of Bennu reach back to a period when the solar system forms from a broad and slowly rotating cloud of gas and dust that collapses under its own gravity. In that early stage, material gathers into a dense disk surrounding the young sun. Temperatures near the centre remain high enough to melt and vaporize many compounds, while the outer regions stay cool, allowing more delicate materials to survive. Within these cooler zones, tiny grains made of carbon silicates and metal-rich compounds drift freely, collide gently, and stick together through electrostatic forces. Over long intervals, these grains grow into clusters large enough to attract additional material through gravity, forming the building blocks of asteroids. Bennu belongs to this group of objects whose components are among the most primitive materials preserved from that early time. The asteroid's carbon-rich composition indicates that it forms in the cooler outer sections of the disk, where molecules containing carbon can persist without being broken apart by heat. These molecules bind to mineral grains, creating complex structures that later become part of larger bodies. The early solar system remains a turbulent environment where collisions are common, and many small aggregates break apart as they grow. The pieces that survive settle into new paths, continuing their slow accumulation of dust. Within this environment, Bennu's earliest material experiences only mild heating, preventing the complete alteration of its carbon-bearing minerals. This preservation allows the asteroid to retain important clues about chemical conditions that existed before planets formed. As materials continue to orbit the Sun in the protoplanetary disk regions, begin to separate according to temperature and density. Closer to the Sun, minerals that withstand high heat dominate. Farther out, fragile grains containing carbon water-bearing compounds and organic material settle into stable paths and continue assembling into larger bodies. These regions become sources for many primitive asteroids, and Bennu's characteristics suggest it forms from material in one of these cooler zones. The asteroid's dark surface and low reflectance indicate the presence of carbonaceous compounds that originate in these early regions. These compounds absorb sunlight, strongly affecting both the appearance and thermal behavior of the asteroid. The early solar system also includes the presence of short-lived radioactive isotopes that generate heat when they decay. Larger bodies with significant mass undergo internal warming that alters their initial composition. Smaller bodies like Bennu do not accumulate enough mass to sustain this heating, allowing them to remain mostly unchanged since their formation. As a result, Bennu acts as a preserved sample of the early material that existed before larger planets, differentiated into cores, mantles, and crusts. The shape and properties of Bennu support the idea that it forms from fragments created by collisions involving larger parent bodies. These parent bodies themselves form from earlier aggregates of dust and rock. Over time, some of them grow large enough to experience internal alteration, creating distinct layers of rock and mineral. When collisions occur, they release fragments into space that contain both processed and unprocessed material. Bennu appears to belong to a group formed mainly from unaltered or lightly altered fragments, suggesting that the original parent body includes significant portions of primitive material. In the early solar system, gravity and motion work together to organize material into bands. Certain regions collect more small bodies, leading to frequent collisions. These collisions shape the sizes of surviving fragments and determine which objects remain stable enough to continue orbiting without breaking apart. Bennu's composition indicates that it comes from a region where impacts do not generate enough heat to erase the chemical signatures of its original material. Instead, the fragments maintain their earlier structure and continue along paths determined by gravitational interactions with nearby bodies. As time progresses, these fragments drift outward or inward depending on how sunlight warms their surfaces and how collisions alter their momentum. Bennu's journey likely begins far from its current orbit, in a zone where carbon-rich material forms in abundance. From there, slow gravitational nudges move it through regions where the distribution of material varies according to solar distance. This path brings Bennu into contact with different conditions while preserving the mineral forms that trace back to the earlier stages of solar system development. The asteroid's material includes mineral grains that contain signs of interaction with water, suggesting that its parent body forms in a region where ice and rock coexist. When early asteroids grow large enough, ice trapped within them can melt due to internal heat produced by radioactive decay. This water reacts with surrounding minerals, forming hydrated compounds that preserve chemical signatures of these interactions. Bennu contains such materials, indicating that the early parent body undergoes some level of water-related alteration before breaking apart. The presence of these hydrated minerals provides evidence that Bennu's earliest components come from an environment where water plays a role even if liquid water does not exist on Bennu itself. During formation, dust grains settle into layers within the protoplanetary disk, and these layers develop distinct compositions based on distance from the Sun. Bennu's carbon-rich nature places it firmly within the zone containing the earliest organic compounds. The asteroid carries these materials through billions of years of orbiting the Sun, experiencing only minor changes at its surface due to micrometeorite impacts and solar radiation. Its interior remains insulated from significant heating, allowing ancient deposits of minerals and organic compounds to remain intact. The asteroid's current structure, often described as a rubble pile, supports the idea that it forms from loosely bound fragments. These fragments join together after the parent body breaks apart, settling into a configuration stable enough to survive but not tightly compressed. This structure allows scientists to infer details about early solar system conditions, including the distribution of materials, the frequency of collisions, and the processes that assemble small bodies. Bennu's origins also reflect the broader patterns of planetary formation. The early solar system forms through hierarchical growth in which small grains combine to form larger bodies, and those bodies undergo further collisions and aggregation to form planetesimals. Some of these planetesimals merge to create planets while others remain as asteroids. Those that avoid intense heating preserve the earliest chemical and physical features of the protoplanetary disk. Bennu belongs to this preserved population, making it a valuable window into the past. The asteroid's current composition retains records of early chemical reactions involving carbon-water-related minerals and silicate materials. These reactions occur during the period when the Sun is young, and the solar system environment remains filled with gas that gradually dissipates. As this gas disperses, asteroid orbits stabilize, and the remaining material settles into long-term paths. Bennu's material follows this pattern, transitioning from early chaotic motion to the more stable orbit it occupies today. Throughout this history, Bennu's composition stays largely unchanged. The limited heating and gentle collisions that affect its earliest form do not erase the mineral signatures that scientists rely on to understand early solar system chemistry. These preserved signatures reveal the temperatures, chemical pathways, and physical conditions that define the formation period. They offer insight into how carbon-bearing compounds assemble within the disk, and how they survive long enough to be incorporated into larger bodies. Bennu serves as a representative sample of this early material, carrying it through time without losing the essential characteristics that trace back to the formation of the solar system. By examining its origins within this ancient environment, scientists gain a clearer picture of how planets form, how water-bearing minerals emerge, and how organic compounds survive during the earlier stages of development. The gradual inward migration of Bennu begins after its earliest material settles into a stable but distant orbit, where fragments of the parent body continue to circle the Sun. Over long spans of time, these fragments experience small pushes produced by sunlight and gravitational encounters that shift them from their original paths. Bennu, composed of dark, carbon-rich material that absorbs much of the sunlight it receives, warms significantly during its daytime and releases heat during nighttime in a way that produces a faint but persistent recoil. This thermal recoil, acting continuously across countless rotations, slowly alters its orbit and draws it closer to the inner regions of the solar system. These changes remain too small to observe within short periods, yet over thousands to millions of years, they accumulate into measurable shifts that bring Bennu from its birth region toward the more densely studied environments near Earth. The inward migration also reflects the gravitational interactions Bennu experiences when passing near larger bodies. Each close encounter exerts a slight pull that changes the direction of the asteroid's motion, adjusting the orbit's shape and its inclination relative to the plane of the solar system. These events occur infrequently but repeat throughout Bennu's long history. Over extended intervals, the combined effect of these encounters produces gradual movement toward a region where near-Earth asteroids follow paths influenced by both solar radiation and planetary gravity. In this inward progression, Bennu experiences variations in solar intensity as its distance from the Sun changes. Closer to the Sun, the higher temperatures increase the strength of thermal forces, amplifying the rate of inward drift. Farther from the Sun, the cooling reduces this influence, creating a cycle in which the overall trend still moves inward, even though local speed varies. These cycles do not produce dramatic jumps. Rather, the motion remains calm, slow, and entirely governed by the physical processes that have shaped small bodies since the earliest stages of planetary formation. As Bennu continues its migration, the distribution of material around it changes. In distant regions, fragments of dark carbonaceous bodies dominate, while the inner regions contain a mix of silicate-rich objects and remnants of early collisions involving rocky materials. Bennu maintains its structural characteristics throughout this transition because its low mass prevents internal heating or significant alteration. Its rubble-like structure, composed of loosely bound pieces of rock and mineral, remains intact even as the asteroid travels into zones where solar radiation becomes stronger. This structure insulates the internal material, preserving the ancient chemical signatures present since the earliest formation. The inward journey exposes Bennu to more frequent interactions with micrometeorite-sized particles that travel along similar or intersecting orbits. These tiny impacts modify the surface by chipping off small grains, producing fresh surfaces that gradually darken again under exposure to solar radiation. This constant renewal of the surface layers shows how Bennu slowly adapts to the changing environment while preserving most of its original composition. As Bennu approaches the inner regions, gravitational interactions with larger bodies become more significant. The orbits of Earth, Mars, and Venus exert cumulative influences that cause the asteroid's path to shift in small, steady increments. Each gravitational encounter alters the orbit slightly, creating a new trajectory with a similar shape but a different orientation. These adjustments continue until Bennu occupies a path that intersects the region of near-Earth space, where its distance from Earth occasionally becomes small enough to enable detailed observation by spacecraft and telescopes. During this migration, the asteroid retains its loose internal structure. Some rubble pile asteroids experience internal rearrangement when heated by sunlight or struck by impacts, but Bennu's moderate size and relatively gentle interaction history allow it to remain stable. The internal gaps between fragments persist, creating a configuration that responds to gravitational forces as a cohesive object despite the loose arrangement of its components. This stability supports reliable modelling of Bennu's long-term migration patterns and its response to thermal and gravitational influences. When sunlight reaches Bennu in the inner regions, the asteroid's dark surface absorbs much of the energy. The absorbed heat increases the temperature of boulders and regolith, creating a stark contrast between the illuminated and shadowed areas. As Bennu rotates, heat flows across the surface in a predictable pattern, giving rise to thermal expansion and contraction that maintain the thermal recoil force responsible for inward drift. This force remains gentle but becomes more pronounced as solar intensity increases. The inward migration also reflects how the distribution of mass within the asteroid influences its motion. The centre of mass determines how Bennu responds to gravity, and how its rotation interacts with external forces. Small shifts in surface material caused by impacts or thermal cracking can alter the rotation slightly. Because the rotation and orbit are linked through thermal processes, any such change contributes to slow but measurable adjustments in the migration rate. Even so, these factors remain within predictable bounds, allowing scientists to reconstruct Bennu's migration history with a high degree of confidence. While Bennu's path moves inward, other bodies travel outward due to similar thermal and gravitational influences. The balance between inward and outward movement within the population of near-Earth asteroids reflects the dynamic nature of the solar system, as a place shaped by constant but subtle changes. Bennu's migration illustrates this balance, showing how small bodies respond to forces that operate over immense timescales. This movement toward the inner regions brings Bennu into environments where precise measurements become possible. Spacecraft observe Bennu's shape, rotational period, and spectral properties, providing data that supports models of thermal drift. These models reveal that the asteroid has migrated a significant distance over millions of years, carrying with it the chemical record of its early formation region. The gradual approach toward Earth's orbit allows researchers to refine predictions of future paths and understand the potential for close encounters. The study of Bennu's inward migration also highlights how the early solar system evolves from a chaotic environment filled with collisions into a more stable system, where small bodies follow predictable paths. Bennu's presence in its current orbit is the result of countless small changes that accumulate over long periods, reflecting the calm and steady processes that shape orbital architecture. Throughout this journey, the asteroid experiences no sudden shifts or violent transformations. Instead, its migration remains an example of how subtle physical forces guide the motion of carbon-rich bodies from distant regions into the inner solar system. The interplay between sunlight, gravity, and rotation continues to define Bennu's path as it travels within regions accessible to spacecraft and observation platforms. This inward progress marks a transition from the environment of its formation to the region where its structure, surface, and composition can be studied in fine detail, offering insight into the preserved materials that trace back to the earlier stages of solar system history. The surface landscape of Bennu presents a terrain shaped by low-gravity ancient fragmentation and the gentle processes that act upon small bodies over long spans of time. Its exterior consists of loose rocks, fractured boulders, and fine grains arranged in patterns that reflect both the asteroid's history and the physical environment in which it travels. Because Bennu's gravity is extremely weak, it cannot compress its surface material into a smooth layer. Instead, fragments remain loosely arranged, held together primarily by gravity, and at smaller scales by contact forces between grains. This creates an uneven surface where slopes, ridges, and clusters of rubble appear across the asteroid, revealing a body that behaves as a collection of pieces rather than a single solid mass. Observations from spacecraft show that Bennu's shape resembles a slightly flattened sphere with a raised equatorial ridge. This form results from the combination of rotation and the distribution of material. As the asteroid spins, centrifugal forces move loose fragments toward the equator, creating a band of accumulated debris that circles the midsection. This ridge contains rocks of various sizes, from fine grains to boulders several meters in diameter, all resting in precarious arrangements made possible by the asteroid's low gravity. The equatorial region thus becomes a prominent feature that shapes the distribution of material across the surface. The areas near the poles appear steeper and contain slopes that would be unstable on Earth but remain stable on Bennu because the gravitational pull is so weak that even large rocks remain in place. The surface boulders show signs of repeated minor impacts from grains and small fragments travelling through space. These microcollisions gradually wear down exposed edges, creating surfaces that appear rounded or fractured, depending on the mineral properties and internal structure of each boulder. Some rocks display cracks formed by thermal stresses. As Bennu rotates, the sunlit side warms while the opposite side cools, creating temperature differences that cause expansion and contraction. Over repeated cycles, these stresses weaken the rock and eventually generate cracks that divide larger pieces into smaller fragments. These fragments then shift across the surface, moving into depressions or joining clusters of rubble elsewhere. The distribution of fine-grained material across Bennu reflects a combination of impacts, thermal cracking, and movement driven by rotation. During each rotation, loose grains may migrate downslope under the influence of Bennu's weak gravity, settling into hollows and low-lying areas. These accumulations form pockets of regolith that contrast with the surrounding boulder fields. Because the surface lacks a significant atmosphere, grains remain exactly where they fall, unless disturbed by impacts or slow movement caused by the asteroid's rotation. The texture of the regolith indicates that it consists of particles from different depths and histories. Some grains are ancient fragments that have remained on the surface for long intervals, while others originate from deeper layers brought upward by impacts. The mix of materials offers clues about the internal composition of Bennu, revealing mineral types that formed under varying conditions. The overall darkness of the surface results from carbon-rich compounds present in many of the rocks and grains. These compounds absorb most incoming sunlight, affecting the thermal behaviour of the landscape and influencing the asteroid's migration through space. The surface also contains scattered depressions that resemble small craters. These features formed when tiny projectiles struck the asteroid at high speeds. Because Bennu is a rubble pile asteroid, impacts do not always produce the deep, well-defined craters seen on larger and more cohesive bodies. Instead, some impacts dislodge material that either rebounds outward into space or lands back onto the surface in new arrangements. The result is terrain that displays subtle impact features rather than large, sharply defined craters. Some surface depressions may be regions where material shifted due to internal movement rather than direct impacts. The low gravity allows internal fragments to settle or shift slightly when thermal or mechanical stresses occur. These movements can cause slight changes in the surface level, producing depressions or raised areas that reflect the flexible nature of the asteroid's structure. The surface also includes unusually bright or reflective rocks that differ from the darker material dominating most of Bennu. These bright fragments likely originate from collisions with other bodies, or from deeper layers that contain minerals with different reflective properties. Their presence among the darker material provides evidence that Bennu contains a mixture of fragment types, assembled from a parent body that includes both primitive carbon-rich components and more reflective mineral phases. The surface slopes vary across the asteroid, with some regions presenting steep gradients that challenge conventional ideas about stability. On Earth, such slopes would be unstable under the pull of stronger gravity, but on Bennu, large rocks remain balanced on inclines because the gravitational pull is hundreds of thousands of times weaker. This allows the landscape to maintain features that appear improbable from a terrestrial perspective. The weak gravity also means that surface material moves slowly. A rock displaced by a minor impact may roll only a short distance before settling. Fine grains drift into stable positions, but do not form dunes or wind-shaped structures, because no atmospheric forces act upon them. Movement occurs only when driven by impacts, rotation, or thermal expansion and contraction of the surface. The asteroid's central ridge also affects the distribution of material by creating zones where centrifugal forces are slightly higher. Over long intervals, this results in rocks and grains moving toward the equator. This migration creates a pattern in which the equatorial region contains a denser concentration of large boulders than the polar areas. The shape of the ridge further indicates that Bennu's rotation remains stable, allowing surface processes to continue without sudden shifts in orientation. The lack of an atmosphere means that temperature changes occur rapidly during each rotation. The landscape experiences heating and cooling cycles that shape surface rocks through thermal fatigue. These cycles contribute to the gradual breakdown of larger boulders into smaller fragments that then join the regolith. The fragmented rocks create a surface that appears rough at every scale, from small grains to large boulders. The interplay of dark material and occasional bright fragments gives the landscape subtle variations in reflectance. The patterns of light observed from orbit reveal differences in mineral content, grain size, and the maturity of surface material. Mature surfaces tend to be darker due to prolonged exposure to solar radiation, while freshly exposed surfaces appear slightly brighter. Some regions of the asteroid display clusters of exceptionally large boulders that rise above the surrounding terrain. These features may have formed from the reaccumulation of fragments after an ancient collision shattered the parent body. The presence of these boulders provides insight into the internal structure, suggesting that Bennu contains a mix of coarse and fine material assembled into a loosely bound configuration. In some areas, the boulder distribution hints at subsurface voids or density variations that influence how the surface settles. The surface landscape thus reflects Bennu's long history of gentle but persistent processes. Over billions of years, thermal cycling, micro-impacts, internal shifting and rotational influence shape the terrain without erasing the ancient signatures preserved within the rocks. Each region of the surface represents a layer of the asteroid's past, providing access to material that formed in the earliest days of the solar system. Bennu's landscape remains stable within the conditions of its environment, maintaining features that reveal its origin as a rubble pile body composed of primitive carbon-rich material. Surface activity on Bennu includes a subtle and infrequent process in which small particles lift from the exterior and drift away before settling back or dispersing into space. This activity remains gentle, reflecting the weak gravitational environment and the limited forces acting on the asteroid's surface. Observations from spacecraft reveal that particles range from fine grains to small pebbles, each propelled by mechanisms that operate at scales unique to a rubble pile body with low cohesion. The events occur without sudden bursts or violent eruptions. Instead, they appear as brief releases of material that respond to thermal changes, impacts from tiny fragments, or shifts within the loose surface layers. Because Bennu lacks an atmosphere, any particle that rises from the surface follows a path defined by gravity, sunlight, and the initial momentum gained at the moment it detaches from the regolith. Some particles fall back onto the asteroid after completing arcs determined by Bennu's modest gravitational pull. Others achieve enough velocity to drift away entirely, although only a small number reach escape speed. Most of the activity reflects the interaction between sunlight and surface material. When Bennu enters its daytime, sunlight warms the outer layers of rock and regolith. The heating causes expansion in minerals that hold together small grains. As the asteroid rotates and the affected regions enter nighttime cooling contracts, these same minerals, repeated cycles of expansion and contraction, create stresses that gradually weaken bonds between fragments. When the stress grows strong enough, tiny pieces of material may detach and release upward. This process, known as thermal fatigue, shapes many small bodies that lack thick atmospheres or strong internal cohesion. On Bennu thermal, fatigue operates across the entire surface, but its effects become more noticeable in regions where sunlight strikes directly at high angles. In these areas, temperature changes are more intense, resulting in stronger stresses within exposed rocks. These stresses create cracks that deepen over time. Once the cracks reach a critical size, pieces of material detach and move slightly above the surface. Some particles dislodge in response to the vibration caused by micrometeorite impacts. When tiny grains travelling through space collide with the surface, they create small shock waves that propagate through the loosely bound material. These vibrations may be enough to free grains that already sit on unstable slopes or rest on other fragments with weak contact points. Because Bennu's gravity is weak, even a minimal disturbance can cause grains to lift. After rising, they either fall back into new positions or drift outward depending on the angle and energy of the initial disturbance. Another possible mechanism for particle release involves the rapid heating of darker material. Bennu's carbon-rich surface absorbs much of the sunlight it receives. As a result, some areas warm more quickly than others. The differential heating can drive small bursts of volatile release if certain minerals contain trace amounts of compounds that respond to temperature changes. Although Bennu does not contain abundant volatile materials, even minor releases may produce enough force to lift fine grains from the surface. These occurrences remain within observed expectations for carbon-rich asteroids and align with the scale of surface activity recorded during spacecraft visits. The launching of particles may also relate to the internal motion of Bennu's loosely bound components. Because the asteroid behaves as a rubble pile, internal fragments can shift slightly over time as they respond to the tidal forces generated during close planetary encounters, or to gradual structural settling caused by rotation. These internal shifts may cause surface slopes to adjust. When this happens, grains located on steep surfaces may begin to slide or hop outward, creating short-lived particle ejection events. The behavior of particles after ejection varies with size. Larger pieces tend to follow simple ballistic paths, rising and falling in predictable arcs. Smaller particles may remain suspended in slow motion for extended periods because the gravitational pull is too weak to cause rapid descent. Some particles drift far enough to travel several meters above the surface before returning. Only a tiny fraction achieve the velocity needed to escape Bennu entirely. These escaped grains contribute to the dust population that surrounds near-Earth space, although their influence remains negligible on large scales. Spacecraft observations indicate that the number of particles ejected during each event remains low. The events do not produce plumes or widespread dust clouds. Instead, the activity appears as isolated and quiet releases that affect only small sections of the surface. This pattern suggests that Bennu's particle ejection is driven primarily by localized conditions rather than global processes. The activity provides insight into how rubble pile asteroids evolve. The release of small particles indicates that the asteroid's surface layers remain dynamic, even in the absence of strong external forces. Over long intervals, this dynamic behavior may lead to gradual rearrangement of surface material. Grains that dislodge from higher elevations travel into lower regions, adding to pockets of fine regolith. Larger fragments that fall back into place contribute to the constant reshaping of slopes. These movements preserve Bennu's overall structure while allowing subtle variations in surface texture and distribution of material. The gentle activity also influences the reflectance of different regions. Areas that experience frequent particle motion may display slightly brighter surfaces because freshly exposed material has not yet undergone the darkening caused by prolonged exposure to solar radiation. In contrast, regions with stable surfaces become darker and smoother over time. The differences in reflectance observed across Bennu reflect this interplay between particle ejection, surface renewal, and exposure age. Some particles that rise from the surface may interact with Bennu's gravitational environment in complex ways. Because the asteroid rotates and has an irregular shape, the gravitational field varies across different regions. This variation affects how particles fall back or drift. Some grains may follow curved paths that lead them to settle far from their original positions. These movements contribute to the transport of material across the surface, helping to explain the distribution of fine-grained pockets and the presence of unexpected mineral fragments in regions far from their source. The activity recorded on Bennu demonstrates how small bodies respond to the combination of thermal processes, micro-impact and structural dynamics. Although the events are subtle, they reveal the sensitivity of rubble pile asteroids to minor forces. Over millions of years, such processes may alter the orientation of surface materials, influence patterns of regolith development, and contribute to the slow transformation of the asteroid's outer layers. Yet the essential composition and overall structure remain intact, allowing Bennu to preserve ancient material beneath a surface that experiences constant but gentle motion. These observations help explain how near-Earth asteroids may shed small amounts of material as they orbit the Sun. The interplay between Sun-like gravity and internal structure defines the scale and frequency of these ejection events. Bennu's activity remains well within the expected range for a body of its size and composition, illustrating the balance between preservation and gradual surface evolution that characterizes many small bodies in the inner solar system. The thermal environment on Bennu arises from the interplay between sunlight surface material rotation and the vacuum of space, creating a cycle that governs the temperature patterns and physical behavior of the asteroid's outer layers. Because Bennu lacks an atmosphere, sunlight reaches the surface without scattering warming exposed rocks and grains directly. As the asteroid rotates, each region experiences a full sequence of heating and cooling that repeats with a rhythm set by Bennu's rotation period. This cycle shapes the physical processes that occur on the surface, influences the structural stability of rocks, and contributes to the slow evolution of the asteroid's orbit through the gentle force generated by thermal radiation. At the start of Bennu's daytime sunlight strikes the surface at low angles, producing a gradual increase in temperature across the illuminated region. The dark carbon-rich material absorbs a large fraction of the incoming energy, which causes the surface to warm quickly compared with objects made of more reflective minerals. Because Bennu's rotation is rapid with each full turn, lasting only a little more than 4 hours, the warming period does not last long. Even so, the exposed rocks reach temperatures high enough to generate strong gradients between the sunlit and shadowed sides of boulders. These gradients create internal stresses as minerals expand in response to heat. As the sunlit region moves toward local noon, the temperature rises further, reaching a peak before the rotation carries that region into decreasing light. This rise and fall produce a daily pattern in which the surface experiences strong thermal fluctuations. The magnitude of these fluctuations depends on the thermal properties of the material. Bennu's regolith has low thermal conductivity, meaning heat does not easily travel downward into deeper layers. As a result, the temperature change remains concentrated within the outermost parts of the surface, which undergo rapid expansion during heating and contraction during cooling. This repeated cycle weakens rocks over time through a process known as thermal fatigue, gradually breaking them into smaller fragments that join the surrounding regolith. When Bennu rotates into nighttime, the absence of sunlight causes the warmed surface to radiate heat back into space. Without an atmosphere to trap or redistribute energy, cooling occurs efficiently. Temperatures drop quickly and the surface becomes significantly colder than regions that still receive sunlight. The contrast between day and night temperatures can cause sufficient stress to propagate cracks within boulders. Over extended intervals, these cracks deepen, eventually dividing larger rocks into smaller pieces. The thermal environment therefore plays a central role in shaping the landscape. These temperature cycles also influence the orbital path through the thermal recoil force that develops when the warm surface emits infrared radiation. Because the rotation and the orientation of the asteroid determine the direction in which heat is released, the recoil exerts a small push that gradually shifts the orbit over long periods. This push is more pronounced when sunlight is stronger and surface temperatures higher. As Bennu moves closer to or farther from the Sun within its elliptical orbit, the magnitude of the thermal force changes accordingly. The cycle therefore becomes an essential contributor to the asteroid's migration across the inner solar system. The equatorial region of Bennu experiences the most intense temperature swings because it remains in sunlight for a larger portion of each rotation than the polar regions. As centrifugal forces move loose material toward the equator, the accumulation of rocks and fine grains affects the thermal response of this band. Thick layers of regolith insulate deeper material, allowing the uppermost grains to heat and cool more rapidly than those beneath. The resulting temperature gradients create stresses at the interfaces between different grain sizes and compositions. These stresses help explain the presence of cracked boulders and the distribution of regolith pockets across the equatorial ridge. By contrast, the polar regions receive sunlight at lower angles, producing milder temperature variations. Rocks in these regions experience less thermal stress compared with those near the equator. As a result, boulders near the poles may display fewer cracks or signs of thermal breakdown. The difference between equatorial and polar heating leads to varied patterns of surface evolution across the asteroid. Some areas remain relatively unchanged over long intervals, while others undergo more frequent fragmentation. The thermal environment also shapes the behaviour of particles that detach from the surface. During daytime, the warming of grains may cause certain minerals to expand, releasing fine particles from cracks or loose material. When the surrounding area cools during nighttime, these grains may become mobile, drifting slightly downslope under the influence of gravity or settling into depressions. The cycle maintains a dynamic but gentle movement of surface material that does not disrupt the overall structure of Bennu, but contributes to subtle shifts in its exterior appearance. The heating patterns also depend on Bennu's irregular shape. Some surface regions face the sun directly during rotation, absorbing energy at higher rates, while others remain in shadow for longer durations. These variations create a patchwork of temperature profiles that evolve as the asteroid moves along its orbit. The resulting complexity influences how scientists model the thermal recoil force, requiring accurate measurements of the shape rotation rate and surface properties. The presence of bright reflective fragments scattered across Bennu adds further variation. These fragments absorb less sunlight, creating small zones where temperature changes differ from the surrounding dark material. Such variations may influence the behaviour of nearby grains, contributing to local differences in thermal fatigue. Over long periods, the thermal environment helps redistribute fine particles across the surface. Warmer regions may experience more frequent particle release, allowing grains to migrate into cooler depressions where they accumulate. This process contributes to the formation of smooth patches of regolith that contrast with surrounding boulder fields. These smooth patches offer insight into the long-term effects of thermal cycling on the asteroid's exterior. The thermal cycles also affect the mechanical stability of rocks. Some boulders sit in positions where slight changes in temperature could shift their balance. Over many cycles, the stresses within these rocks may lead to small adjustments that alter their orientation or position. Although such movements occur slowly, they represent an important mechanism through which rubble pile asteroids evolve. The thermal environment therefore acts as a primary force shaping Bennu's surface and influencing its orbit. The daily cycle of heating and cooling drives the breakdown of rocks, the release of particles, and the gradual rearrangement of material. The long-term cycle associated with the asteroid's orbit around the Sun modifies the magnitude of these effects, ensuring that Bennu's evolution remains steady and continuous. Despite the persistence of these forces, the essential composition and structure of the asteroid remain preserved, allowing Bennu to carry ancient material through space, with only minor changes at the surface. These thermal processes illustrate the balance between energy input from the Sun and the physical response of primitive material in a low-gravity environment. The behaviour of Bennu under these conditions provides insight into how carbon-rich bodies survive billions of years of exposure to sunlight, how they maintain their structure despite ongoing thermal stress, and how they respond to long-term orbital evolution. Moving inward from the surface, Bennu's interior reveals a structure defined by loose aggregation, rather than solid rock forming what scientists describe as a rubble pile body. This structure develops after the parent asteroid breaks apart in an ancient collision, sending fragments of varying sizes into independent orbits that later reassemble under gravity. The resulting object contains boulders, fine grains, and empty voids arranged in a configuration that remains stable only because Bennu's gravity is extremely weak. Unlike larger bodies that compress under their own weight to form distinct layers, Bennu lacks the mass needed to create significant internal pressure. As a consequence, the interior retains a porous architecture with spaces between fragments and a distribution of material that reflects the conditions present when the pieces first came together. This porous nature explains many of Bennu's physical properties, including its low density, its gentle response to impact, and its tendency to rearrange surface material without causing catastrophic structural failure. The internal fragments vary in size, composition and shape, representing pieces of the parent body that survived the initial breakup. These fragments remain loosely connected, forming an interior in which rocks touch at irregular points rather than forming a continuous matrix. The arrangement allows Bennu to absorb impacts more effectively than solid bodies. When a small object strikes the surface, energy transfers through the loose interior without generating large shock waves. Instead, the energy dissipates through minor movements of fragments, reducing the potential for widespread structural disruption. The lack of high internal pressure also means that the fragments do not deform significantly over time. They retain the shapes and mineral features they possessed when they joined the rubble pile. This preservation provides scientists with a rare opportunity to study material that has not experienced the extensive alteration that occurs in larger asteroids or planetary bodies. The interior therefore serves as a repository of ancient mineralogical and chemical signatures, protected by the outer layers and insulated from extreme temperature fluctuations by the poor thermal conductivity of the loosely packed material. Inside, Bennu voids between fragments create paths for small movements of material. These internal adjustments may occur slowly, as rotation thermal cycles or external forces shift the positions of individual pieces. Because the asteroid's gravity is weak, even slight changes in balance can cause local rearrangements. These movements contribute to surface events such as the slow drifting of grains or the settling of boulders into new positions. The interior does not act as a rigid structure, but rather as a flexible assembly that responds to subtle changes in load distribution. Over long periods, this flexibility helps Bennu maintain its overall shape while adapting to external influences. The asteroid's distinctive shape, including its raised equatorial ridge, reflects the internal distribution of mass. As Bennu rotates, centrifugal forces push loose material outward, especially toward the equator. This process requires internal pathways that allow fragments to shift slightly and accommodate the new distribution. The presence of voids facilitates this movement, enabling the asteroid to reach a stable configuration without requiring deformation of solid rock. The ridge formation indicates that the interior structure supports significant migration of material while maintaining cohesion. Gravity binds the fragments tightly enough to prevent disassembly, yet loosely enough to allow gradual internal reorganization. These characteristics classify Bennu as a transitional object between small aggregates and more coherent bodies. Its interior properties also influence the behavior of seismic waves. When impacts occur, the loose interior dampens vibrations, quickly preventing long-range propagation. This damping effect reduces the likelihood of fractures spreading through the asteroid and contributes to Bennu's long-term stability. The interior may also contain larger voids that form as fragments settle into configurations that leave open spaces between them. Such voids can affect how mass distributes within the asteroid and how gravity behaves across its surface. Variations in the gravitational field influence how particles fall back after ejection events and how material accumulates in specific regions. Internal voids also reduce the overall density of Bennu, aligning with measurements that show the asteroid's density to be significantly lower than that of typical rocky bodies. These voids represent a form of preserved structure that provides additional information about the formation and reaccumulation process following the breakup of the parent body. Bennu's interior likely contains a mixture of finer grains and larger blocks, with size distribution influenced by the collision that formed the parent body's fragments. Larger blocks may originate from deeper layers of the parent asteroid, while fine grains may represent surface material or pieces produced during fragmentation. The presence of both types within the interior indicates that the reaccumulation process collected fragments from various regions of the parent body, mixing material of different histories into a single object. This mixture creates a complex internal structure in which mineral types and grain sizes vary widely, influencing both mechanical and thermal properties. The porous nature of the interior also affects how heat flows through Bennu. Because gaps between fragments impede the transfer of thermal energy, the asteroid's deeper layers remain insulated from temperature changes occurring at the surface. This insulation helps preserve ancient minerals and organic compounds within the interior, protecting them from the thermal stresses that break down rocks on the surface. The retention of these materials offers a rare window into early solar system chemistry, as they have remained largely unchanged since their formation. The interior structure likewise affects how Bennu responds to torques generated by sunlight. When the surface absorbs and re-emits heat, the resulting recoil can alter the rotation rate over long intervals. The porous internal structure changes how the asteroid redistributes mass in response to these torques. Small shifts in the positions of internal fragments may affect the rotation, slightly creating a feedback process in which the internal and external behaviours interact. Although these changes occur extremely slowly, they help shape the long-term evolution of the asteroid's rotation and orbital path. The interior composition also provides clues about the presence of minerals that formed in the presence of water. Hydrated minerals, which contain water incorporated into their crystal structure, suggest that parts of the parent body experience conditions where water interacted with rock. These minerals likely reside within the interior of Bennu, preserved from alteration due to the insulating nature of the rubble pile structure. Their presence demonstrates that the parent body hosted environments where water-related chemical processes occurred, even if Bennu itself does not contain liquid water. Moving farther inward, the density of fragments may increase slightly, as gravity draws heavier components closer to the centre. However, the overall structure remains unconsolidated, with no evidence of a solid core or distinct internal layering. Instead, Bennu's interior retains a continuous distribution of fragments without sharp boundaries. This arrangement aligns with observations of similar rubble pile asteroids and supports models of formation based on reaccumulation after a major collisional event. The central region likely contains a mix of coarse blocks and fine grains held together by gravity. The absence of strong internal compression means the fragments remain largely unchanged from their original state. The preservation of this material makes Bennu an especially valuable object for scientific study. Its interior serves as a natural archive of early solar system processes, containing evidence of the chemical, thermal, and mechanical conditions that shaped planetesimals. The loose structure voids and diversity of fragment sizes combine to create a record of events that extend back billions of years, offering insight into the processes that gave rise to larger bodies and the evolution of small asteroids in near-Earth space. Deeper inside Bennu, the mineralogy begins to reveal the chemical story preserved within its carbon-rich fragments, showing how early solar system material remains intact inside a rubble pile asteroid. The minerals present in Bennu trace their origins to the cooler regions of the protoplanetary disk, where temperatures allowed carbon-bearing compounds, silicates, and metal-rich grains to coexist without extensive alteration. These minerals assembled into small aggregates that later became part of the parent body from which Bennu formed. When this parent body broke apart, fragments of varying size and composition rejoined to create the asteroid as it exists today. Because Bennu never accumulated enough mass to undergo significant heating, its minerals escape the melting recrystallization and internal differentiation that larger bodies experience. As a result, the interior retains primitive minerals that record the conditions present in the earlier stages of solar system development. The most notable feature of Bennu's mineralogy is its abundance of carbonaceous material. This carbon resides in multiple forms, including complex organic compounds and mineral-bound carbon that reflects the cold, chemically rich environment where these materials formed. Some of these compounds derive from molecules that condensed onto dust grains when the solar system was still forming. These early molecules survived incorporation into larger aggregates because the parent body's interior remained cool enough to preserve them. Bennu's low-density structure helps protect these compounds from destruction by heat, allowing fragile materials to endure for billions of years. Silicate minerals found within Bennu include olivine pyroxene, and other rock-forming components that represent the earlier solid phases to condense from the protoplanetary disk. These minerals form microscopic crystals within fine grains as the disk cools. Over time, these grains merge into larger pieces through collisions and electrostatic forces, eventually becoming parts of asteroids. The presence of these silicates in Bennu indicates that the parent body contained material from a wide compositional range mixing both carbon-rich and silicate-rich fragments. The silicates within Bennu may contain traces of iron and magnesium that reflect the temperature and chemical environment at the time of formation. Some minerals appear as fine-grained aggregates that form under low-temperature conditions. These aggregates preserve microscopic features that record chemical pathways involving water, carbon dioxide, and other compounds present in the early disk. Their presence in Bennu suggests that the parent body hosted regions where water-bearing minerals formed through reactions between rock and water. These reactions require environments where water existed either as ice or as liquid within protected interior regions. When the parent body later fragmented, these hydrated minerals became incorporated into Bennu's structure. Because Bennu's interior remains insulated from significant heating, these minerals have remained unchanged since their incorporation, offering direct evidence of early water-related chemistry. Carbonate minerals found within Bennu provide additional clues about ancient interactions between water and rock. These minerals typically form when carbon dioxide interacts with water and certain types of rock-producing crystalline structures that incorporate carbon. Their presence within Bennu indicates that portions of the parent body underwent chemical processes involving water. Although Bennu does not contain liquid water today, the minerals preserved within it record conditions in which water once influenced the composition of the parent body. This information helps establish the broader context of early solar system chemistry, where water and carbon-bearing materials played significant roles in shaping the mineral structures found in primitive asteroids. Another important class of minerals within Bennu includes phyllosilicates, which form through the alteration of primary silicates by water. These minerals have layered structures that hold water within their crystal lattice. Their presence indicates that the parent body experienced conditions where water interacted with silicates at low temperatures, preserving the chemical signatures of these reactions without altering the overall structure of the asteroid. In Bennu, these phyllosilicates remain intact because the rubble pile configuration protects them from intense heating or pressure. The variety of mineral types within Bennu demonstrates that the parent body contained diverse materials that formed under different conditions. Some minerals originate in the colder outer regions of the disk, while others form slightly closer to the Sun where temperatures allow for more extensive chemical reactions. When the parent body experienced its collisional breakup, fragments containing these minerals mixed together before reaccumulating into the present-day asteroid. This mixing allowed Bennu to inherit a broad range of mineral types, creating a complex composition that reflects multiple stages of early formation. The interior grains also contain traces of metal-rich particles that formed in high-temperature regions close to the young Sun. These metal grains travelled outward through the protoplanetary disk, mixing with cooler material in regions where primitive asteroids assembled. Their presence within Bennu indicates that the parent body incorporated material from a wide radial range within the disk. Because metal grains resist alteration better than many other minerals, they remain preserved inside the rubble pile interior. Some fragments may contain mineral inclusions that predate the solar system itself, known as pre-solar grains. These grains originate in the outer layers of ancient stars and survive the formation of the protoplanetary disk. They retain isotopic signatures that differ from material formed within the solar system. If present within Bennu, these grains would offer direct evidence of the environments that existed before the Sun formed. Bennu's carbon-rich nature increases the likelihood of preserving such grains, although the overall quantity remains low. Their survival within the interior reflects the protective nature of the rubble pile structure, which shields fragile minerals from destructive conditions. The mineralogy of Bennu also includes compounds that respond to exposure to sunlight and cosmic radiation. Over long periods, radiation alters the surface layers of some minerals, darkening them or changing their chemical composition. However, these alterations remain limited to the uppermost layers of the asteroid. Deeper within the interior, minerals remain shielded from radiation, preserving their original chemical properties. This contrast helps scientists determine how long certain regions of the surface have been exposed and how radiation influences the gradual evolution of Bennu's outer layers. Another feature of Bennu's mineralogy is the presence of fine-grained matrix material that binds larger mineral fragments. This matrix contains carbon-rich compounds, hydrated minerals, and tiny crystals that act as a record of early solar system processes. The matrix forms under low-temperature conditions and retains a high degree of porosity, allowing Bennu's interior to maintain its loose structure. The presence of this fine-grained material indicates that the parent body underwent gentle alteration without experiencing extensive heating or pressure. Moving inward, the concentration of carbonaceous material may increase slightly as larger fragments settle toward the center. However, the differences in distribution remain modest because Bennu's gravity is too weak to promote significant segregation of minerals. Instead, the interior preserves a largely uniform mixture of mineral types arranged in a loosely bound configuration. This uniformity reflects the reaccumulation process after the parent body's breakup, and the absence of strong forces that would otherwise separate minerals by density. The mineral assemblage observed within Bennu reveals the remarkable preservation of early solar system history. The presence of phyllosilicates carbonates, silicates organic compounds, and possibly pre-solar grains shows that the asteroid contains material that records chemical pathways involving water, carbon, and rock. Each mineral type contributes to a detailed picture of the environments where they formed. The rubble pile structure protects these minerals, allowing them to endure without significant alteration. Bennu therefore serves as a preserved chemical archive carrying evidence of the processes that influence planetesimal formation and the conditions that existed before the planets took shape. The study of these minerals offers insight into the origins of carbon, the distribution of water-bearing materials, and the chemical diversity of the early solar system. Farther inward, evidence of hydrated minerals reveals that Bennu carries material shaped by interactions with water that occurred long before the asteroid formed its present structure. These hydrated minerals, which contain water bound within their crystal frameworks, require specific conditions to develop. They form when liquid water or warm water-rich fluids interact with primary silicates on a parent body, large enough to trap heat for limited periods. Although Bennu itself does not host liquid water, the minerals preserved within it indicate that its parent body once contained regions where water circulated through porous rock. This circulation produced chemical reactions that altered minerals, recording the presence of water in a way that persists even after billions of years. The hydrated minerals remain protected within the interior because Bennu lacks the mass needed to generate temperatures high enough to destroy them. The fine-grained matrix present in many fragments contains phyllosilicates, which form through the alteration of silicates by water. These minerals develop in low-temperature environments where water interacts with rock at levels insufficient to melt or deform the parent material. Their layered structures hold water within their crystal arrangements, trapping chemical signatures from the moment of formation. Because the interior of Bennu remains insulated by poor thermal conductivity and the asteroid's low mass, these minerals remain largely unchanged. Their preservation provides strong evidence of ancient water activity. Another class of hydrated minerals present within Bennu includes carbonates. These minerals typically form when carbon dioxide-rich fluids react with rocks in the presence of water. The formation of carbonates requires stable environments where temperature and pressure remain suitable for crystallization. Their presence signals that the parent body once held liquid water in protected interior regions, allowing carbon-bearing solutions to interact with mineral surfaces. The carbonates within Bennu carry the chemical record of these processes, representing conditions that may have existed in the early solar system, when heat from radioactive isotopes temporarily warmed the interiors of primitive bodies. These early water-related processes did not erase the original composition of the parent body, but gently modified it, creating a mixture of primary silicates and secondary minerals. When the parent body later broke apart, fragments containing these hydrated minerals were preserved. They became part of Bennu's loosely bound structure, allowing scientists to study the hydration history of the parent body without the complications caused by extensive heating or pressure. These hydrated minerals therefore provide a link between Bennu and a time when water played a more active role in shaping the composition of small bodies. The distribution of hydrated minerals within Bennu may vary across the interior. Fine-grained regions preserve higher concentrations of phyllosilicates, while larger boulders may contain isolated veins or pockets of altered material. These patterns reflect the complex structure of the parent body, where water likely moved along fractures or permeated porous layers. The diversity of hydrated minerals suggests that the parent body contained multiple environments with different degrees of water exposure. Some regions may have experienced brief but significant interactions, while others remained unaltered. The rubble pile nature of Bennu mixes these materials, preserving the full range of hydration histories within a single asteroid. The presence of hydrated minerals influences Bennu's mechanical properties. Phyllosilicates tend to be softer and weaker than primary silicates, contributing to the asteroid's porous structure. These minerals help bind fine grains into cohesive aggregates that move and settle within the interior. Their presence may also affect how heat flows through the asteroid. Because hydrated minerals have different thermal properties compared with unaltered silicates, the distribution of water-related phases influences the overall response to thermal cycling. Although the differences are subtle, they contribute to the intricate thermal behavior observed at the surface. The preservation of hydrated minerals also implies that Bennu's interior has not undergone significant compaction or heating since the asteroid formed. If the interior experienced strong thermal alteration, the water bound within these minerals would have escaped, leaving behind anhydrous phases. Instead, the minerals remain intact, confirming that Bennu has existed as a cold, low-pressure environment since its reassembly. This stability helps maintain the chemical signatures that provide insight into water activity in the early solar system. Some fragments within Bennu may also contain minerals such as magnetite, which can form through reactions involving water. The presence of magnetite suggests that the parent body experienced oxidation processes facilitated by water-rich environments. These minerals offer additional clues about the temperature and chemical conditions present when the parent body altered. The formation of magnetite requires controlled conditions, indicating that water interactions occurred in regions with stable temperatures. The combination of phyllosilicates, carbonates, and magnetite presents a detailed record of water-related processes in the early solar system. These minerals form over distinct temperature ranges and reflect changes in water composition and rock chemistry. Their presence within Bennu demonstrates that the parent body hosted a variety of environments, some of which supported prolonged interactions between water and rock. The survival of these minerals highlights the importance of rubble pile asteroids in preserving these early chemical pathways. Hydrated minerals also influence the reflectance of Bennu's surface. Areas that contain exposed hydrated material may appear slightly brighter or exhibit spectral features associated with water-bearing compounds. Spacecraft observations detect these signatures, confirming their presence both at the surface and within subsurface layers. However, the majority of hydrated minerals remain buried within the interior, protected from the surface processes that darken exposed rock. The distribution of hydrated minerals also relates to regolith development. Fine-grained material containing phyllosilicates may break apart more easily under thermal stress, contributing to the formation of loose regolith. This material may settle into depressions or drift toward the equator, affecting the overall landscape. The presence of hydrated grains within the regolith indicates that internal fragments have been brought to the surface through impacts or internal shifts, mixing hydrated material with unaltered fragments. The study of hydrated minerals within Bennu provides insight into the evolution of early planetesimals. The parent body must have existed long enough for heat from radioactive isotopes to melt or mobilize water trapped within ice. Water then interacted with surrounding rock-altering minerals before the body cooled. Once the parent body fragmented, the altered material became part of Bennu. This sequence of events reflects the chemical and physical processes that govern the earlier stages of asteroid formation. Hydrated minerals also help scientists understand the distribution of water in the early solar system. Their presence suggests that water existed in regions where carbon-rich materials formed. This combination of water and carbon may have influenced the development of organic compounds, providing conditions favourable for complex chemical reactions. The preservation of hydrated minerals in Bennu therefore contributes to broader questions about the origin of water and organics in the solar system. Moving toward the centre, the concentration of hydrated minerals remains mixed within the rubble pile interior. Because the asteroid lacks stratified layers, hydrated material occurs alongside unaltered grains. This mixture reflects the heterogeneous structure of the parent body and the chaotic nature of the reaccumulation process. Yet despite the lack of layering, the minerals retain their chemical integrity because the interior remains cold and stable. The preserved hydrated minerals represent a long-lived record of ancient water activity, providing insight into how water shaped the mineralogy of early planetesimals and contributed to the diversity observed in carbon-rich asteroids. Bennu's interior therefore serves as a unique archive of water-related chemistry, offering a window into the history of one of the fundamental components of the early solar system. Within the inner regions of Bennu, measurements of mass density and gravitational behaviour begin to reveal how its loose internal structure governs every aspect of the asteroid's physical response to external forces. Bennu's total mass is modest for an asteroid, reflecting its small size and the large amount of empty space distributed throughout the interior. Because mass determines the strength of the gravitational field, Bennu produces only a faint gravitational pull, barely strong enough to hold its fragments together. Yet this weak gravitational field sets the conditions for all surface and internal processes, shaping the movement of particles, the stability of boulders, and the slow rearrangement of material within its rubble pile core. The measurement of Bennu's mass comes from observing how the asteroid influences the trajectory of nearby spacecraft. As a spacecraft approaches and enters Bennu's gravitational environment, its motion shifts slightly in response to the asteroid's pull. Careful tracking of these changes allows scientists to calculate Bennu's mass with precision. When combined with measurements of its volume, this value produces an estimate of density. Bennu's density is significantly lower than that of solid rock, indicating the presence of large void spaces within its interior. This low density defines Bennu as a porous body, whose internal fragments do not fill the available volume completely. The gravitational field across Bennu's surface varies subtly due to the irregular distribution of mass within the rubble pile. Some regions contain clusters of large boulders that create stronger local gravity, while other regions contain voids or fine-grained material that contribute to weaker gravity. These variations influence how particles fall back when they are lofted from the surface and how regolith accumulates in depressions. They also shape the stability of slopes, determining where material tends to move and where it remains in place. Because Bennu's gravity is weak, even small disturbances can dislodge surface fragments. A pebble that shifts on a slope may continue moving slowly across the surface before finding a stable resting place. These movements reflect the balance between gravity rotation and internal structure. Bennu's gravitational behaviour helps explain the raised equatorial ridge, where centrifugal forces during rotation nearly counterbalance the pull of gravity. This balance allows loose material to migrate outward and accumulate in a band around the equator. The strength of Bennu's gravitational field also determines escape velocity, the speed required for a particle to leave the surface and drift into space permanently. Because the escape velocity is extremely low, even small impulses from impact's thermal expansion or internal movement can lift tiny grains above the surface. Most particles eventually fall back, but a few achieve sufficient velocity to escape. The measurement of escape velocity helps scientists understand the particle ejection events observed during Bennu's daytime heating cycles. Variations in gravity across the surface also influence how sunlight-driven forces act on the asteroid. When sunlight warms the surface and the warmed material radiates heat, the resulting recoil contributes to the Yarkovsky effect, which slowly alters Bennu's orbit. The magnitude and direction of this recoil depend on the distribution of heat across the surface, which in turn depends on how the internal structure affects thermal conduction. Areas where large boulders lie beneath thin regolith layers may absorb and retain heat differently than regions where fine-grained material forms a thicker insulating layer. These differences influence the long-term orbital evolution of the asteroid. Bennu's rotation interacts with its gravitational field in complex ways. As the asteroid spins, centrifugal forces push material outward. In regions where centrifugal force nearly equals gravitational attraction, surface fragments can become mobile. This balance is especially pronounced near the equator where the raised ridge forms. The gravitational field across this ridge may differ from surrounding regions due to the accumulation of material. Internal voids beneath the ridge may further influence gravity by creating areas of slightly reduced mass concentration. These variations help explain the uneven distribution of boulders and the presence of steep slopes that remain stable despite conditions that would lead to collapse on larger bodies. Differences in density across the interior affect how Bennu responds to small torques generated by sunlight and planetary tides. Over long periods, these forces can alter the rotation rate. If the rotation changes slightly, the centrifugal forces acting on surface material also change, which may lead to slow rearrangement of fragments. This interplay between rotation and internal mass distribution reveals how rubble pile asteroids maintain long-term stability while still experiencing subtle shifts in their physical properties. Bennu's gravitational environment also influences the behavior of internal fragments. Because the gravitational pull is weak, blocks within the interior may shift under small stresses without causing large-scale deformation. These movements occur slowly, driven by changes in temperature, external impacts, or minor structural adjustments as fragments settle into more stable configurations. The presence of voids allows for these movements by providing space for fragments to shift without encountering significant resistance. Over long intervals, these internal shifts may alter the distribution of mass, slightly influencing the gravitational field at the surface. Despite this flexibility, the overall mass distribution remains consistent enough for scientists to model Bennu's motion with high accuracy. The reaccumulated structure that defines the asteroid appears to have reached a stable configuration in which large-scale changes are unlikely. The gravitational field reflects this stability through its predictable behavior during spacecraft encounters. Bennu's density, calculated through mass and volume measurements, places it among the least dense carbon-rich asteroids studied closely. This low density confirms the presence of voids that occupy a significant portion of the interior. The voids reduce the average density and allow the asteroid to maintain its loosely bound structure without collapsing under its own weight. This structure suggests that Bennu forms from fragments of a parent body that experienced a major collision, resulting in the rapid assembly of a low-density aggregate held together primarily by gravity. The gravitational field also provides insight into Bennu's resilience. When struck by impacts, the rubble pile interior absorbs energy through movement rather than through large-scale fracturing. This absorption reduces the likelihood that Bennu would split apart under moderate impacts. Instead, the interior adjusts, dispersing the energy through rearrangements of fragments. This property contributes to Bennu's long-term survival in near-Earth space, where impacts from small grains remain common. Gravitational measurements also help scientists understand the distribution of hydrated minerals and carbon-rich material. If heavier fragments containing dense minerals concentrated toward the center, the gravitational field would reflect this distribution. However, observations indicate that the interior remains relatively uniform in composition, with no significant concentration of dense material at the core. This uniformity supports models suggesting that the parent body contained a wide mixture of minerals and that the reaccumulation process created a consistent distribution of fragments throughout the interior. The interaction between mass density and gravity influences Bennu's potential hazard to Earth. To assess long-term impact probabilities, scientists must understand how small forces affect the orbit. Accurate measurements of mass and density allow models to predict how Bennu will respond to gravitational encounters with Earth and other planets. These encounters can adjust the orbit slightly, influencing the asteroid's position over decades and centuries. Understanding the gravitational behaviour also assists in evaluating how spacecraft interactions, such as sample collection, might affect the asteroid. Removing material from the surface changes the mass distribution slightly, but Bennu's weak gravity and flexible interior minimise the effect. The asteroid adjusts without significant disruption. These observations illustrate the delicate balance that defines Bennu's physical state. The combination of low mass, high porosity, and gentle gravitational pull creates a unique environment where ancient materials remain preserved within a structure that responds subtly to external forces. This balance allows Bennu to maintain its integrity while undergoing slow changes driven by thermal processes, impacts, and gravitational interactions. Bennu's gravitational behaviour therefore represents a crucial piece of the puzzle in understanding the dynamics of rubble pile asteroids. By studying mass density and gravitational variations, scientists gain insight into how small bodies evolve, survive, and interact with surrounding space. As Bennu moves along its orbit, the long-term assessment of its potential to approach Earth closely depends on understanding how small gravitational forces, thermal processes, and rotational behaviour influence its trajectory over decades and centuries. Because Bennu's mass is low and its structure porous, even faint external influences can adjust its orbit measurably over extended periods. Predicting these adjustments requires careful tracking of every known factor that alters the asteroid's motion. These factors include gravitational interactions with Earth and other planets, the gentle push produced by sunlight as the surface warms and cools, and the internal distribution of mass that determines how Bennu responds to these forces. Impact probability assessment therefore begins with precise orbital data collected through repeated observations from ground-based telescopes and spacecraft. Each observation refines the orbital path, narrowing the range of possible future positions. Because Bennu approaches Earth periodically, these close passes provide opportunities to reduce uncertainty by measuring slight shifts in trajectory. When the asteroid moves through regions where Earth's gravity influences its motion, its path may change subtly, creating new trajectories that branch into multiple possibilities. Scientists use detailed models to calculate these possibilities, identifying key intervals known as close approach windows. Within these windows, small differences in Bennu's position can lead to widely different outcomes in later decades. The thermal recoil produced by Bennu's surface plays a significant role in long-term trajectory changes. As sunlight warms the asteroid during its daytime, the warm surface emits infrared radiation, producing a small push known as the Yarkovsky effect. This push acts consistently as Bennu rotates, gradually altering its orbit. The direction and strength of the recoil depend on Bennu's rotation surface properties and the distribution of heat. Unlike gravitational forces, the thermal recoil is sensitive to the internal structure, because variations in density and material arrangement influence how heat flows through the asteroid. As a result, predicting Bennu's future path requires accurate knowledge of both external forces and internal characteristics. Over decades, the small thermal push may move Bennu slightly inward or outward, relative to its previous orbit, altering the timing of encounters with Earth. These timing changes determine whether the asteroid passes through gravitational keyholes, narrow regions in space, where Earth's gravity modifies the orbit in ways that increase the likelihood of future close approaches. Keyholes are defined by precise alignments of orbital timing, distance, and direction. If Bennu passes through a keyhole during a close encounter, it may follow a trajectory that leads to a later approach near Earth. However, most keyholes are extremely small, often spanning less than a few hundred meters. Because Bennu's orbit can be predicted with increasing precision, scientists can determine whether the asteroid is likely to cross any keyholes during known close encounters. When Bennu passed near Earth during previous cycles, spacecraft observations provided detailed measurements that reduced uncertainty in the orbit. These measurements allow scientists to compute the probability of future close approaches. The resulting probabilities remain extremely small for the foreseeable future. Even so, tracking these probabilities requires ongoing monitoring because small forces continue to influence the trajectory. The gravitational environment of the inner solar system also affects Bennu. Interactions with Venus, Mars and Earth produce subtle directional changes in the orbit. These gravitational encounters, when combined with the thermal recoil and rotational behaviour, create a complex interplay that shapes long-term predictions. Because gravitational forces act on Bennu's centre of mass variations in the internal distribution of fragments, may influence how the asteroid responds to planetary encounters. The rubble pile nature of Bennu means that internal movements could slightly modify the centre of mass over long time spans. Although these movements remain small, they contribute to the overall uncertainty in long-term trajectories. Impact probability assessment therefore involves a careful balance between known forces and expected variations. Scientists simulate millions of possible future orbits to determine how Bennu may behave under slightly different conditions. These simulations account for the uncertainties in the asteroid's position, mass distribution, thermal properties, and rotation. By projecting these possibilities forward, scientists identify the range of outcomes for future close approaches. The probabilities associated with these outcomes help determine whether Bennu poses any meaningful hazard over long periods. Bennu's rotation also plays a role in its long-term orbital evolution. As the asteroid absorbs and emits heat, the resulting thermal torque may change the rotation rate slightly. These rotational changes influence how sunlight acts on the surface, which in turn affects the direction and magnitude of the thermal recoil. Over centuries, these interactions create a feedback cycle in which rotation affects orbit, and orbit affects rotation. Although the changes remain small, they must be incorporated into long-term predictions. In addition to thermally driven forces, small impacts from micrometeorites contribute minor adjustments to Bennu's motion. Each impact delivers a small impulse which may alter the asteroid's velocity. Over long periods, these impulses accumulate, though their overall effect remains small compared with thermal and gravitational influences. Still, the cumulative effect must be considered when assessing long-term impact probability. Close approaches to Earth provide opportunities to refine these assessments. When Bennu passes relatively near Earth, observations capture its position and velocity with higher accuracy, reducing uncertainty in the orbital path. These refinements allow scientists to better determine whether Bennu may experience gravitational encounters that lead to increased or decreased future hazard. Because Bennu's orbit intersects the region where Earth travels, periodic close approaches will continue as long as the orbital arrangement is maintained. Impact probability assessments therefore remain dynamic, requiring periodic updates as new data becomes available. The rubble pile structure of Bennu also influences how scientists model the effect of gravitational encounters. A loosely bound interior behaves differently from a solid rock when subjected to tidal forces during close passes. Although Bennu's encounters with Earth occur at distances insufficient to cause major tidal distortion, even small forces may shift internal fragments. These shifts could modify the orientation of the centre of mass slightly, which may change how Bennu responds during future encounters. Such effects remain subtle, but are important for high-precision modelling. Because Bennu's gravitational environment is weak, the redistribution of mass within the interior may occur slowly, driven by thermal cycling or small impacts. These changes do not alter the overall structure of the asteroid, but contribute to slight variations that affect long-term predictions. Understanding these processes helps reduce uncertainty in impact probability assessments. Evaluating the potential threat posed by Bennu requires acknowledging the limitations of long-term prediction, while recognizing the high precision of current measurements. With each new observation, uncertainty shrinks, enabling models to predict Bennu's location decades into the future with increasing confidence. The largest source of uncertainty remains the effect of the thermal recoil, which varies with surface properties. As spacecraft data provides more detail about these properties, predictions become more reliable. The assessment of Bennu's potential threat shows that although the asteroid approaches Earth periodically, the probability of impact in the near future remains very low. This low probability reflects the combination of precise measurement, stable orbital evolution, and favourable gravitational encounters. The asteroid's path continues to be refined through ongoing monitoring, ensuring that long-term predictions remain as accurate as possible. By examining how sunlight gravity rotation and internal structure influence Bennu's trajectory, scientists gain insight into the broader processes that govern the movement of near-Earth asteroids. Bennu serves as a model for understanding how small bodies evolve in dynamic environments, how hazards are assessed, and how subtle forces shape the future paths of objects that travel near Earth. As Bennu enters the region where spacecraft approach the outer environment, begins to include elements shaped not only by natural forces, but also by the careful planning required to observe and navigate around a small low-gravity asteroid. The arrival of NASA's mission marks a transition from remote sensing to direct observation, allowing the asteroid's surface shape and motion to be measured with unprecedented precision. The approach phase begins long before the spacecraft comes within close range. As the spacecraft travels through interplanetary space, it adjusts its trajectory using small engine burns designed to guide it toward Bennu's orbit without introducing unnecessary velocity differences. Because the spacecraft must match Bennu's speed and direction to enter a stable proximity, the planning relies on highly accurate predictions of the asteroid's motion. These predictions depend on continuous observation and refined orbital models that account for gravitational influences, solar radiation, and the thermal recoil that alters Bennu's path gradually over time. As the spacecraft draws nearer, it begins to detect Bennu as a faint point of reflected sunlight against the dark background of space. This initial detection marks the start of a sequence of navigational steps that bring the spacecraft closer with each passing day. Instruments designed to measure brightness and motion help determine the exact location of the asteroid, allowing navigators to correct the spacecraft's course as needed. Because Bennu's gravity is extremely weak, the spacecraft must navigate using its own propulsion system, rather than relying on gravitational capture. The approach sequence requires a series of careful maneuvers to ensure that the spacecraft arrives at a distance where it can maintain stable flight relative to Bennu. Once in this region, the spacecraft begins collecting detailed data about the asteroid's shape, rotation, and surface properties. The first observations reveal that Bennu has an irregular, slightly diamond-shaped profile with a prominent equatorial ridge. These shape measurements play a critical role in planning the later phases of the mission, particularly because the terrain includes large boulders, steep slopes, and regions of fine-grained material that behave differently under weak gravity. As the spacecraft circles Bennu at a safe distance, it captures images from multiple angles. These images help construct a three-dimensional model of the asteroid, allowing researchers to understand the volume density distribution and gravitational field. The spacecraft also uses remote sensing instruments to measure surface reflectance, temperature variations, and mineral signatures. These early observations confirm that Bennu contains carbon-rich material consistent with models of primitive asteroids. The mapping phase requires the spacecraft to remain in precise relative motion with Bennu. Because the asteroid rotates rapidly, completing a full turn in a little over 4 hours, the spacecraft must adjust its orbit to maintain stable viewing conditions. The weak gravitational environment means that even small external forces such as pressure from sunlight can alter the spacecraft's trajectory. Navigators compensate for these forces with gentle engine burns, ensuring that the spacecraft remains in the correct position for detailed scanning. As the mission progresses, the spacecraft moves into closer orbits, allowing its instruments to collect higher resolution data. These orbits are extremely low compared with those used for planetary observation, sometimes bringing the spacecraft within a few kilometers of Bennu's surface. At this proximity, the irregular gravitational field becomes more noticeable. Variations caused by internal voids and uneven distributions of rock create subtle changes in the spacecraft's motion. Continuous monitoring of these changes provides insight into Bennu's internal structure and mass distribution. The mapping stage also reveals thermal behaviour across the surface. As Bennu rotates different regions warm and cool, creating a cycle of temperature variation that affects how the surface responds to sunlight. The spacecraft's thermal instruments detect these variations, providing data that helps refine models of the Yarkovsky effect. Understanding this thermal behaviour improves predictions of Bennu's long-term orbital evolution. As the spacecraft gathers more data, it begins searching for a location where it can safely collect a sample. This process requires evaluation of many factors, including boulder distribution, slope stability, regolith depth, and lighting conditions. Because Bennu's surface is dominated by large rocks, finding a location free of hazards becomes one of the mission's most challenging tasks. The mapping process identifies several candidate sites, each evaluated for safety and scientific value. Some regions contain fine-grained material that appears suitable for sample collection, while others contain larger rocks that pose risks to the spacecraft. The approach and mapping phases require constant coordination between navigation engineers, scientists, and mission planners. Each new observation updates the models used to guide the spacecraft. Because Bennu's gravitational environment offers little assistance in maintaining stable trajectories, the spacecraft must rely on precise control systems to avoid unexpected drift. This controlled flight represents a unique aspect of exploring a small asteroid where natural forces that dominate planetary missions play only a minor role. As the spacecraft moves closer to selecting a sample site, it enters a series of reconnaissance phases designed to capture detailed images of the target locations. These images reveal the fine structure of surface material, including small pebbles, cracks in larger boulders, and patches of fine-grained regolith. The weak gravity allows loose material to settle in ways that differ from terrestrial environments. Some regions appear deceptively smooth from a distance, but contain rocks large enough to disrupt the sampling mechanism. The spacecraft's instruments also measure the reflectance spectra of the surface near the candidate sites. These spectra indicate the presence of carbon-rich minerals, hydrated minerals, and fine-grained matrix material. The combination of surface properties and mineral signatures helps determine which sites will provide the most scientifically valuable sample. The approach phase continues as the spacecraft performs rehearsals of its sampling maneuver. These rehearsals involve descending toward the asteroid without making contact, testing the spacecraft's ability to navigate within meters of the terrain. Each rehearsal refines the control systems and provides confidence that the spacecraft can execute the final descent safely. Because the gravitational pull is so weak, the spacecraft must use precise thruster firings to maintain the correct position. Even a slight drift could lead to contact with hazardous boulders. As the approach sequence draws to its final stages, the spacecraft achieves a level of understanding of Bennu's shape, gravity, rotation, and surface that far exceeds the initial predictions. These measurements confirm that Bennu is a rubble pile asteroid with significant porosity, abundant carbon-rich material, and surface conditions shaped by thermal cycling and particle ejection events. The mapping and approach phases demonstrate how exploration of small asteroids requires techniques different from those used for planets or moons. The spacecraft remains in constant motion relative to Bennu, adjusting repeatedly to maintain stability in an environment where gravity offers little guidance. This controlled navigation becomes essential for achieving the mission's objectives, ensuring that the spacecraft can observe the asteroid from all angles and choose a sampling site with confidence. As the mission prepares for the sampling maneuver, the results of the approach and mapping phases provide the foundation for understanding Bennu in detail. The data collected during this time reveal the complexity of the asteroid's surface, the distribution of organic-rich material, the structure of the interior, and the thermal environment that shapes its evolution. These observations lay the groundwork for the successful retrieval of material that will later be examined on Earth, offering insights into the formation and evolution of the solar system. The moment of sample acquisition begins long after the spacecraft has completed its mapping and rehearsal phases, marking a transition from observation to direct interaction with Bennu's surface. Because the asteroid's gravity is extremely weak, the spacecraft must rely entirely on its guidance system to descend in a controlled manner. The process involves a sequence of precisely timed steps, starting with a slow departure from a safe orbit and continuing through a careful approach toward the chosen sampling site. Each step responds to Bennu's irregular shape variable terrain, an uneven gravitational field ensuring that the spacecraft remains steady as it approaches the surface. The descent begins with the spacecraft positioning itself above the target site and orienting its sampling arm outward. This sampling arm contains a mechanism designed to collect material by releasing a brief pulse of gas that lifts fine grains from the surface into a collection chamber. Because Bennu's regolith remains loosely bound, the sampling strategy depends on this gentle approach. The spacecraft slowly reduces its altitude, adjusting its trajectory continually to maintain alignment with the target area. The weak gravitational environment means that even a small deviation could place the spacecraft in a position where it might encounter large boulders or uneven slopes. As the spacecraft moves closer, its navigation system uses images of the surface to refine its path. These images show the arrangement of rocks, grains, and shadows guiding the descent toward a region where the sampling arm can make contact without obstruction. The spacecraft reduces its speed to a very slow rate, allowing the sampling mechanism to touch the surface with minimal force. Because Bennu's gravity provides little resistance, any excessive momentum could push the spacecraft away from the surface or cause unwanted movement. The sampling arm reaches downward and touches the regolith using a quick controlled motion. At the moment of contact, the mechanism releases the pulse of gas. This pulse disturbs the fine-grained material at the site, causing grains to rise into the chamber. The gas pulse lasts only a brief moment, yet it provides enough force to lift particles that have remained loosely packed on the surface. These grains represent a mix of hydrated minerals, carbon-rich compounds, fine silicates, and other fragments that originated within the parent body long before Bennu formed its current structure. During this contact, the spacecraft must maintain stability, despite the lack of gravity. The sampling arm absorbs the reaction force generated by the gas pulse, ensuring that the spacecraft does not drift or rotate unexpectedly. The controlled mechanism allows the spacecraft to collect material without digging or scraping the surface, which would be impractical under the asteroid's conditions. As soon as the sampling arm retracts, the spacecraft fires its thrusters to ascend and move away from the surface. These thruster firings prevent the spacecraft from drifting into nearby boulders or recontacting the surface. The ascent carries the spacecraft to a safe distance where it can evaluate the success of the maneuver. Because the collected sample cannot be inspected directly in space, the spacecraft uses its cameras to observe the sampling chamber. These observations confirm whether the chamber holds enough material for return to Earth. The images reveal fine grains lodged inside the chamber, indicating that the sampling mechanism performed as intended. In some cases, small fragments may protrude from the chamber, as the irregular shapes of the grains cause them to settle in unique arrangements. After confirming the sample's presence, the spacecraft prepares the return capsule. This capsule serves as a protective container for the material during its journey back to Earth. The interior of the capsule remains sealed to prevent contamination and protect the sample from exposure to space. The capsule is designed to withstand re-entry through Earth's atmosphere, carrying the ancient mineral and carbon-rich fragments safely to the surface. The spacecraft maneuvers into a trajectory that positions it for release of the capsule at the appropriate moment. Because Bennu's gravity is negligible, compared with Earth's, the spacecraft must use its propulsion system to transition onto a return path. This path requires precise calculations to ensure the capsule enters Earth's atmosphere at the correct angle and speed. Once aligned, the spacecraft releases the capsule into an independent flight path that directs it toward Earth. The moment of release marks the beginning of the capsule's journey through interplanetary space. It travels quietly, carrying material that records billions of years of solar system history. The capsule remains stable and sealed until it reaches Earth's atmosphere. During atmospheric entry, the capsule experiences intense heating on its exterior, while the interior remains protected. As it descends, its heat shield ensures the sample remains intact. After the capsule reaches lower altitudes, parachutes deploy to slow its descent. The capsule eventually lands in a designated area, where recovery teams retrieve it for transport to specialized laboratories. The sample acquired from Bennu contains a mixture of grains that reflect the asteroid's diverse mineralogical and chemical composition. These grains include carbon-rich particles formed in the early protoplanetary disk hydrated minerals that record interactions with water, and fine silicate fragments that represent the primitive building blocks of the solar system. The sample provides a direct link to conditions that existed billions of years ago, preserved within Bennu's rubble pile interior. The success of the sampling process demonstrates the precise engineering required to interact with a low-gravity asteroid. The spacecraft's ability to match Bennu's rotation, approach the surface safely, and collect material without destabilizing itself reflects the careful planning necessary for such missions. The controlled nature of the sampling maneuver contrasts with the chaotic environment where Bennu formed, illustrating how modern exploration techniques enable the study of ancient material. The sample stored within the return capsule represents a small portion of Bennu's vast supply of primitive material. Yet even this small amount provides valuable information about the mineralogy, organic content, and hydration history of the asteroid. Because the sample originates from a fine-grained region, it contains material from both the surface and potentially deeper layers brought upward by impacts or internal movements. The presence of fine grains increases the likelihood of capturing fragile minerals and organic compounds that would not be preserved in larger rock fragments. The sampling phase concludes with the spacecraft departing Bennu's immediate vicinity. Although it no longer interacts directly with the asteroid, the data collected during the approach, mapping and sampling phases continue to guide scientific understanding. The sample's return to Earth marks the beginning of laboratory analysis where advanced instruments can examine the grains at much finer scales than spacecraft sensors allow. These analyses provide insight into chemical pathways, mineral structures, and isotopic signatures that reveal the history of early solar system processes. The successful acquisition and return of the sample demonstrate the importance of combining remote sensing-controlled descent and precise engineering to study small bodies. Through these methods, scientists gain access to material that has remained largely unchanged for billions of years. The sampling phase therefore represents a critical step toward understanding the origins of carbon water-bearing minerals and the primitive compounds that shape the formation of planets and other bodies. Once the sample from Bennu arrives on Earth, its examination begins in laboratory environments designed to preserve the integrity of the ancient grains. These laboratories provide controlled conditions where temperature, humidity, and atmospheric composition remain constant, ensuring that the delicate minerals and organic compounds do not degrade. The grains within the sample represent material that records the earlier stages of solar system history, preserved inside Bennu's rubble pile interior for billions of years. Because Bennu never experienced high internal temperatures or intense pressure, the material within the sample remains chemically and structurally similar to its original state. Laboratory analysis begins with careful removal of the sample from the return capsule. Specialists open the capsule in a clean environment that prevents contamination from modern air dust or biological material. The grains are transferred into sealed chambers where they undergo initial visual inspection under low-power microscopes. This inspection helps identify grain size distribution, the presence of fine dust, and the general appearance of the material. The grains display a dark color characteristic of carbon-rich asteroids. Some grains contain reflective surfaces that indicate the presence of silicates or metal-bearing minerals. Others exhibit porous textures suggesting that they formed under low-temperature conditions where water interacted with rock. These preliminary observations guide scientists in selecting specific grains for detailed study. The next stage of analysis involves mineral identification. Researchers use techniques such as X-ray diffraction to determine the crystal structures present in each grain. This method reveals the presence of phyllosilicates, carbonates, fine-grained silicates, and other minerals that formed during the early history of the parent body, the patterns observed in the diffraction data provide evidence of low-temperature alteration, supporting the idea that water played a role in modifying the original silicates. Additional instruments measure the elemental composition of grains, using techniques such as electron microprobe analysis. This method determines the concentrations of elements such as carbon, oxygen, magnesium, iron, and silicon within each mineral. The distribution of these elements reflects the chemical environment where the minerals formed. For example, the presence of iron-rich phyllosilicates indicates that oxidation processes occurred in the parent body, while carbon-bearing minerals reveal the abundance of organic compounds in the early solar system. Another important aspect of laboratory analysis involves examining organic molecules preserved within the sample. Researchers extract these molecules using gentle chemical techniques that do not damage fragile structures. These organics include simple carbon-based compounds, as well as more complex molecules that require cold conditions to form. The presence of these organics demonstrates that Bennu carries material analogous to the building blocks that existed throughout the early solar system. Some compounds may record processes that occurred before the Sun formed, reflecting contributions from pre-solar environments, where stars and interstellar clouds produced complex chemistry. Further analysis focuses on hydrated minerals that record ancient interactions between water and rock. Scientists use infrared spectroscopy to identify the specific wavelengths absorbed by these minerals. The absorption patterns correspond to water bound within the crystal structure, indicating the extent of hydration. These results provide insight into the temperature and chemical conditions that existed in the parent body's interior. The hydrated minerals confirm that the parent body hosted environments where water altered the original silicates without causing large-scale melting. Stable isotopes within the grains offer additional clues about their origins. Researchers measure isotopic ratios of oxygen, hydrogen, and carbon to determine the processes that shape the minerals. These ratios reveal whether the grains formed in the outer regions of the protoplanetary disk, where carbon-rich material dominated, or whether they incorporated components from high-temperature regions close to the young Sun. Some isotopic signatures reflect contributions from pre-solar grains that originated in ancient stars and survived the formation of the solar system. The presence of these grains within Bennu's sample provides direct evidence of the diverse materials that contributed to the formation of early planetesimals. Laboratory techniques also allow scientists to examine the microstructure of grains at extremely fine scales. Electron microscopy reveals the shapes, surface textures, and internal layering of minerals. These features provide clues about whether grains experience thermal cycling collisions or gentle alteration by water. The microstructure helps reconstruct the history of each grain, tracing its path from formation in the early solar system to its incorporation into Bennu's rubble pile interior. Some grains contain microscopic pores or fractures that reflect the low-pressure conditions under which they formed. Others display rounded shapes consistent with gentle collision processes. These textures differ significantly from those found in grains subjected to high temperatures or intense pressure, confirming that Bennu's interior preserved the original characteristics of its constituent fragments. The laboratory analysis also examines the distribution of grain sizes in the sample. Fine particles reflect processes such as thermal cracking and micrometeorite impact that occurred near the surface of Bennu. Larger fragments may originate from deeper regions, providing insight into the internal mineral distribution. The combination of fine and coarse grains reveals how impacts, thermal cycling, and internal movements shaped Bennu's interior over long timescales. Another aspect of the analysis involves studying the magnetic properties of the grains. Some minerals retain weak magnetic signatures that reflect the magnetic field present during their formation. These signatures offer clues about the environment of the protoplanetary disk and the presence of magnetic fields around the young Sun. The magnetic data, combined with chemical and isotopic analysis, helps create a comprehensive picture of early solar system conditions. The sample from Bennu also allows researchers to study the role of carbon in early solar system chemistry. The carbon-rich grains contain organic molecules that may represent some of the earliest complex chemical structures. By examining these molecules in their preserved state, scientists can determine how they formed, how they survived space conditions, and how they interact with minerals. This research contributes to understanding how carbon-bearing material may have been transported throughout the solar system and incorporated into larger bodies. Laboratory analysis continues over extended periods as different instruments and techniques reveal new layers of detail. Each grain contains multiple lines of evidence that contribute to a broader understanding of Bennu's history. Scientists compile these observations to reconstruct the sequence of events that formed the minerals, altered them through water-related processes, mixed them within the parent body, and later preserved them within Bennu's rubble pile interior. The careful study of these grains provides insight not only into Bennu, but also into the wider population of primitive asteroids that share similar histories. As researchers complete their analyses, the results contribute to models of solar system formation, helping explain how water carbon and silicate minerals combined to create the materials that eventually formed planets. Bennu's sample plays a central role in testing these models because it contains material that has remained largely unchanged since the earliest stages of development. The presence of hydrated minerals, organic compounds, and primitive silicates reveals the chemical diversity that existed in the protoplanetary disk. These findings help scientists understand how planetesimals formed, how water became distributed throughout the inner solar system, and how organic material survived long enough to participate in later stages of planetary evolution. The laboratory work completes the exploration pathway that began with Bennu's distant orbit and continued through surface mapping and sample collection. The sample provides the innermost layer of understanding, revealing the microscopic and chemical details that cannot be observed from space. By examining the grains in controlled environments, researchers gain a detailed view of the processes that shape the early solar system. The results of these analyses deepen scientific knowledge of how carbon-rich material forms and how primitive bodies preserve the record of ancient chemical pathways. Through the combination of orbital data surface observations and laboratory analysis, the complete study of Bennu demonstrates how small asteroids act as archives of early solar system history, offering insights into environments that existed long before the formation of planets. In the quiet that surrounds the final stage of study, the sample from Bennu rests within controlled laboratory spaces where time moves at a slower and more deliberate pace. Each grain remains still under gentle light, carrying with it the record of distant eras when the solar system first forms from drifting clouds of dust and gas. The laboratories that hold these fragments maintain conditions far more stable than the environment Bennu has known for billions of years. Here, temperature and humidity do not shift abruptly, and no impacts disturb the material. The grains lie protected, allowing scientists to examine them with calm precision. The long journey that begins in the cold outer regions of the early disk now reaches its quietest point. The rubble pile interior that shields Bennu's minerals for so many ages has delivered them safely into human hands. Under microscopes, the grains reveal textures, colours, and structures shaped by ancient processes. Some contain signs of gentle interaction with water preserved in the form of hydrated minerals. Others reflect the presence of carbon that settled on dust grains before planets formed. These materials hold information that can guide understanding of environments long vanished from space. In this silent setting, the grains offer a view into regions where heat, light, and gravity shaped the first solid bodies. The stability of the laboratory allows them to be observed without disturbance, supporting analysis that moves from large fragments to microscopic particles. Each examination adds clarity to the picture of how Bennu forms, how its parent body interacts with water, and how the rubble pile asteroid preserves these early conditions. The steady light within the laboratory mirrors the calm conditions that define Bennu's evolution through space. The sample now rests in a place where its ancient structures can be studied slowly, without the constant motion that defines the environment around an orbiting asteroid. Through this quiet process, the innermost details of Bennu's history become clearer. The grains reveal how carbon-rich material accumulates, how minerals interact with water at low temperatures, and how fragments of a parent body reassemble into a stable configuration that endures for billions of years. The final stage of analysis reflects the gentle passage of time within the laboratory. The grains continue to lie undisturbed, offering their record of early solar system processes to those who study them. In their stillness, they connect the distant past to the present moment, completing the inward journey from the outer regions of Bennu's orbit to the microscopic structures that preserve its history. Through this quiet work, the story of Bennu and the ancient material it carries becomes clearer, allowing understanding to settle gradually and steadily, much like the fine grains that rest within the sample itself.